All right, so the request that I got for review this section was just to talk about how we build y sub p in undetermined coefficient problems. So the example I'll be talking about is us trying to solve some y double prime minus y equal to g of x. And real quick, I'm going to talk about building intuition for how we construct y sub p, and then we'll look at a couple examples. So our goal is to find, I guess I should underline this. Our goal is to find y sub p so that y sub p double prime minus y sub p equals g of x. That's all we want. And so kind of having that goal in mind, the idea that we plug into the left-hand side and what's left over is g of x, leads us to the first rule we made for ourselves when we build y sub p, which is maybe y sub p equal to g of x, or at least kind of similar to g of x, will work for us. So kind of think about if, g was, I don't know, cosine 7x. Then you imagine if you're plugging in y sub p right here, then that's how you create that g of x term that should be left over, because y sub p is on the left side, so if it looks like g, then that'll probably appear on the right side. And of course, that's not the complete answer. So how can that first intuition go wrong? And the first way is with derivatives. So derivatives of g will be left over. So actually just thinking about that same example again, if I've got my cosine 7x right there, and then I plugged in, I think y sub p is cosine 7x, but when I take its derivative, oh, that's actually a bad example. Let's do x squared. Okay, so g was x squared. When I plug in my x squared right there for y sub p, eventually my yp double prime is going to be 2. And so I have this extra term right there that came from the derivative, and that's going to make it so that I can't match what's on the right side. So we're going to include derivatives of g in y sub p. Oops. And we think that that'll help us cancel everything out on the left side so that only what originally appeared in g is left over. And then the second way this can go wrong is if y sub p includes solutions to y double prime minus y, they'll disappear. And so, for example, y double prime minus y has solution e to the x. So let's say I had e to the x right there, and I said, okay, maybe my y sub p is e to the x, then my y double prime would be e to the x. But that's not going to be e to the x. That's going to be 0. Because it solved the ODE, the left-hand side becomes 0, so my leftover g of x that I want to see isn't there. So we just add on powers of x until this isn't a problem. And so hopefully that kind of helps you understand where the intuition for those 3 different rules we had came from. Seeing in just this concrete example of how if you forget to include all your derivatives, or if you have solutions to the differential equation, it's going to make the rules for, it's going to make your guess for y sub p not work out. So in general, we combined these three rules to find our y sub p equals a times something plus b times something plus c times something, so on and so forth, for undetermined coefficient problems. And I just wanted you to kind of get a stronger feeling for why that is, because there seemed to be a bit of confusion about where those y sub p come from. So just a reminder, pick the things that look like g, include the derivatives of g, and then add on powers if you already built that solution to make sure that you aren't kind of repeating yourself and going to cancel things out. So we're just going to practice this with a couple examples. We're going to do y double prime minus y equal to x squared times, let's do an e to the x one first. So just first note, you could solve the left-hand side equal to 0 with a constant coefficients problem. And they're just going to be y1 equal to e to the x and y2 equal to e to the minus x. So since g is equal to x squared e to the x, my first rule says maybe y sub p would be a times x squared e to the x. But to include derivatives, I'm going to go ahead and say, okay, the derivative of x squared e to the x is going to give me 2x e to the x plus x squared e to the x. And so I had started out with an x squared e to the x term, and now I also have an x e to the x term. This one is the same as before, so it doesn't really do anything for me. But now that I have this new term right here, x e to the x, I imagine if I plugged that into y, it would need something to cancel out with in the y double prime. So I'm going to go ahead and take another derivative. And you could take it of everything, but I just took a derivative of x squared e to the x, and I'm just going to get the same thing out of it again. So really, you only have to take a derivative of the new thing. So that's just going to give me 2 e to the x plus 2x e to the x. Yep. And so I got this new term, e to the x, and this x e to the x was a repeat, so it doesn't matter to me. And I imagine if I plug this in, maybe it's going to need something to cancel out with in the end, so I'd better try again, taking derivatives of my new term. Oh, but the derivative of e to the x is just e to the x again. So I didn't need this step. It was enough to stop right there, because this new thing is a repeat. So those don't matter. All that matters is the new things I found. Maybe y sub p should be a times x squared e to the x, but also including these new things, bx e to the x and c e to the x. And I didn't hold on to these 2's because my a, b, and c are unknown. So if I hold on to the 2's, I'm just making a bigger algebra problem for myself. If you had like a 2 right here, you're just going to be holding on to a 2 everywhere you solve for b and c, but it doesn't change your final answer. So I choose to ignore those constants. If that bothers you, just hold on to them. It's okay. They'll go away eventually. And then to get rid of solutions, x squared e to the x wasn't a solution, so it's fine. X e to the x wasn't a solution, so it's fine. But e to the x was. So I'm going to have to go ahead and add on powers of x until I don't have an existing solution anymore. That's going to be up to x cubed. And then from there, you could just plug into ODE to solve A, B, and C. And I'm not going to do that because it's a lot of algebra and not really a good use of your time. I know we're probably like right at 10 minutes by now, but I'm going to go ahead and do another example. Stick around if you want to see it, but it's just going to be more undetermined coefficients. So we're going to use that same y double prime minus y because then I don't have to tell you what the solutions are again. And this time we're just going to practice something that looks like a cosine or sine. So let's do sine of, I don't know, 3x, I guess. So my g is equal to x sine 3x. So I think, oops, maybe y sub p would be equal to a times x times sine of 3x. So to include derivatives, I would look at the derivative of, oh, I don't need my a, x sine of 3x. So let's see, I'm going to hold on to my x, take the derivative of sine, it's just going to give me cosine 3x. Then take the derivative of x is 1, leaves me behind with a sine of 3x. And a 3 would appear here. Tracking those constants doesn't really matter, so you can be sloppy here. But I'll try not to be. So I started with an x sine 3x. Now I've created an x cosine 3x and a sine 3x. So I'm going to have to take derivatives of all those things this time to see what would need to be canceled out in my y sub p. And I don't think I've left myself enough room to do this, but that's okay. We'll just do the cosine and then the sine. So let's see, 3 cosine 3x, when we take the derivative of x, plus 9 times x times sine 3x, when we take the derivative of cosine, and that becomes a minus sign. The pluses and minuses don't really matter, but I'm just going to go ahead and include it anyhow. And then the derivative of sine 3x is going to give me a cosine 3x times 3. And then let's see what we found here. Okay, so my cosine 3x is a new term. My x sine 3x already appeared, so that's not new. And my cosine 3x is the same as this one right there, so it also doesn't matter. It's not new as of that third line. So my only new thing is like a cosine 3x type term. Maybe you would see both the cosine 3x's and combine it to a 6. So that's what I'll do right here. And when I take the derivative of cosine, that just gives me a minus 6 sine 3x. But when I look at that, it's a term that already exists. So I could have stopped right there. It's the same as something I had before. So I think maybe y sub p would be made up of all these new things I found. A times x sine of 3x plus b times x cosine of 3x plus c times sine of 3x plus d. Oh man, I didn't even give myself enough room there. I was writing really stretchy. Bx cosine of 3x plus c times cosine of 3x plus d times sine of 3x. Like that. That captures the 4 different types of terms I found when taking derivatives, and if I kept on taking derivatives, things would just repeat. So that's why I stopped once I stopped creating new terms. And this doesn't overlap with solutions to the ODE. So at this point, we could go ahead and say that this is what we would plug in to solve for A, B, C, and D. I'll go ahead and draw a box around that and a box around our answer there. Since we like propose things along the way, but we really want to emphasize which one was correct. So hopefully those help you have a little bit more intuition for how we build the particular solutions for the constant coefficient problems. If in doubt, nothing's going to go wrong if you just keep on taking down the powers of x until you have every possible derivative that could be created by your function. So I would say do that if you're worried. Like if I saw an x squared term here, I would say, okay, maybe I have to add on an extra x term. It'll just drop out if it's not important. And if you have questions about this, let me know. I know it's a difficult topic. It's really good practice, though, to be able to recognize what solutions can possibly look like. So